Uh, Assalamu alaikum, dear student. I hope you are fine and doing well. Today, our topic is quite important. It's about eigenvalue decompositions. Eigenvalues are used in number of engineering problems, like in communication system, designing of bridges, designing car stereo system, electrical engineering, mechanical engineering. And one of the finest application of eigenvalues and eigenvectors, or I can say eigenvalue decomposition, is right now utilized in Google page rank algorithm that cleverly utilize the idea of eigenvalues and eigenvector in order to search your query, which you are just putting in Google search engine. But no, if I can give you some communication system like eigenvalues were used by Claude Shannon to determine the theoretical limit to how much information can be transmitted through a communication medium like your telephone line or through air. This is done by calculating the eigenvalues and eigenvectors of the communication channel, which can be expressed as a matrix. So, dear student, the eigenvalues are then in a sense, the gain of the fundamental mode of channel, which themselves are captured by the eigenvectors. So these are some of application. Also, these eigenvalues are utilized in also in image compression too. So let us elaborate what does eigenvalues means and what are their corresponding eigenvectors and how one can calculate these eigenvalues and eigenvector. I mean to say eigenvalue decomposition of any matrix A. Let us fundamentally define it. If you have any square matrix and a question arises, does there any column vector in Rn such that if you can multiply this, if you can say this A with any column vector x is equal to scalar multiple of what you call the scalar multiple of x. It means if you multiply a with x is equal to scalar multiple of a in which is lambda times x. If you operate a into x is equal to lambda time, it means x remains same if you apply a on x, but that operation of a on x generate basically lambda. This is consequences of this action of a on x that consequently generate lambda, but the vector x remains same. So if we can say if matrix A act on x, that it is basically stretching the vector x, but it does not change its direction. So the x is an eigen vector of A. Let us consider one example in order to understand what does this meaning of these. Like if you have matrix A and these are two column vectors. If you multiply A with x, then what you will get? 2, 0, if you can take 2 as a common. So 2 into x1. It means if you multiply A with x, x is remain like this is x1 and x is remain same and you just put 2. So 2 is your eigenvalue. Let us say if you multiply a with x2, so if you multiply it with x2, you will get 0 and minus 1. If you take minus 1 as a common, so minus 1, 0 and 1. So 0, 1 again we get x2. So in that case, minus 1 is eigenvalue. So dear student, if you just keep this thing in a v is equal to lambda time v or ax is equal to lambda time x. These are eigenvalues and eigenvector equation. So there are three cases arises. Av is equal to lambda time v. If lambda is greater than 0, in that case your vector will be stretching. Or if lambda is between 0 to in that case there will be a compression. And if lambda is less than 0, in that case your vector will be stretching in negative direction. So this is one of the theorem related to eigenvalues and corresponding their matrix. If A is an n-class n matrix with eigenvalue lambda, then the set of eigenvectors of lambda corresponding together with the zero vector is a subspace of Rn, and this space is called the eigenspace of lambda. Let us take one example. For if you have this matrix A and the eigenvalues are lambda minus 1 and lambda plus minus 1. So if you multiply A with x, what you will get? You will get minus times x, so you will have to bring minus 1 as a common, x into 0. So this will be eigenvalue and corresponding eigenvector is 0 and x. If you multiply A with 0 and y, so in that case you will get 0 and y. If you take 1 as a common, so in that case 1 is eigenvalue and 0 and 1 remain same. A multiply on 0 and y. So ultimately, after multiplying A with this vector, the vector remains same, and this is basically eigenvalues, and this is eigenvectors. So geometrically speaking, if you multiply A with any vector with respect to previous example, A x is 0, A x 0, and it can be written as this column vector can be written as x0 plus 0y. If you operate A on the first vector and then on second vector, what you will get? If you multiply A with x and 0, minus 1 x and 0 plus 1 0y, in that case you can look is corresponding what you call the what it basically perform if we multiply A with B. So if this coordinate before applying A on this coordinate x and y, if you multiply A on this coordinate, so this will give you the resultant minus x and y. Basically, this is the reflection about y-axis. So in that case, we can say these are reflection corresponding to if you multiply if you multiply any vector in R square by the matrix C, it is the corresponding to the reflection to the y-axis in that case. This is geometrical representation of this uh, application of A to any vector in two-dimensional V. So this is one of the eigenvalues. How do you can find out the eigenvalues of any square matrix? So if you have n class n matrix and an eigenvalues of A is a scalar value such that determinant of lambda time I for identity matrix of n class n minus A equal to, or you can say determinant of A minus lambda time equal to 0. In that case, the corresponding eigenvector can be find out through this eigenvalue or eigenvector equation lambda I minus A into x, or you can use A minus lambda type into x equal to 0. So in that case, you can say this one from the definition of eigenvalues problem, Ax equal to lambda time x. This implies Ax is equal to lambda time I of x can be written as this one, or this can be written as lambda into identity matrix minus A into x equal to 0. In that case, this will be a dear student, the eigen basically it has non-zero solution if the determinant of this expression is 0 and the x is basically column vector which is the solution to this homogeneous equation should not be. In that case, the determinant of lambda I minus a is the basically the characteristics equation of A, and it can also be written as determinant of lambda I minus a. It is in the form of lambda to the power n. Basically, it has n cross n column square matrix A. So if you have 2 by 2 matrix, so in that case you will get uh, quadratic equation in term of lambda. Let us elaborate this with the help of some examples. Dear student, let us find out the eigenvalues of this square matrix. So, determinant of lambda I minus a, it means lambda minus 2, 12 minus lambda uh, minus 5, which is plus 5. In that case, if you can take its determinant and put it equal to 0 due to this condition, this one. So in that case, dear student, you would find lambda is equal to minus 1 and 1. These are eigenvalues. So their corresponding eigenvectors, so you will have to use this equation. Lambda 1, uh, I is basically identity matrix of 2 by 2 minus a is your this this matrix a. It means uh, 2 time 2 by 2 identity matrix minus a matrix of 2 by 2. X is x1 and x2 because you have 2 by 2, so you have 2 now equal to 0. Basically, I have to use this equation in order to get some non-zero values of x. So after solving this by using Gauss-Jordan elimination, so you have to say this one. So x1 here we have one uh, free variable t. So x2 is free. In that case, x1 is 4 times t and x2 is t. And we can take t as a common. In that way, t is non-zero. So you have basically the solution 4 and 1. And it has basically this is a, from here, if you can look over here, this is homogeneous system of equation. This is homogeneous system. Also, it has a trivial solution or infinite many solution. But here in this case, in case of eigenvalues and eigenvector, we are interested in non-trivial solution. It means to the infinite many, the possibility of infinite many solution. So again, we corresponding to lambda 2 minus 2, second eigenvalue. So we will use same procedure as we have used in this case. So we will get another x1 and x2. This is 3s. So again, this is a free variable. It means we have infinite many solution corresponding to lambda 2, which is equal to minus 1. So in that case, we have ultimately two eigenvalues corresponding to these two eigenvectors. So let us find another what you call the example. So you have basically the find the eigenvalues and corresponding at eigenvector for the matrix A. What is the dimension of eigenspace of each eigenvalues? So you have a upper triangular matrix. So the characteristics equal lambda minus a lambda I. So I here is 3 by 3. What you call the identity matrix of 3 by 3 minus a. So in that case, you can take its determinant of this expression. So we have 3 by 3 determinant. So we have basically uh, eigenvalues value of multiplicity 3. In that case, we have not distinct eigenvalue. We have repeated eigenvalues, which is lambda is equal to 2. So eigenspace of lambda is equal to 2 lambda I minus 2. You have to put the values lambda over here and multiply this 2 with the 3 by 3 matrix and then subtract it from matrix A, which is this one 3 by 3 matrix. So ultimately, X is basically x1, x2, x3, and this is homogeneous system of equation. So if you have solved it, so in that case you have two free variables s1 and t. So you have the solution to this homogeneous system 1 0 0 0 0 1. and it has infinite magnitude solution because S and T are free variable. In that case, we have two independent vector vector 1 and 0 and 0 0, and we have two free variable. In that case, the dimension of eigenspace will be 2, corresponding to lambda is equal to 2. So if an eigenvalue lambda 1 occur at multiplicity root k time for the characteristics polynomial, then lambda 1 has multiplicity k. Uh, Another result, the multiplicity of an eigenvalue is greater than or equal to the dimension of its eigenspace. In case if like if you can say this one, the multiplicity over here is 3, and you can say the multiplicity is always greater than the dimension of eigenspace, but the dimension of this eigenspace is 2. In that case, multiplicity is 3 and eigen dimension of eigenspace is 2. So let us take another example. Find the eigenvalues of A and find the basis for the each of the corresponding eigenspace. Like you have very big matrix and you can take this characteristics equation and put it equal to 0. So in that case, you have four eigenvalues uh, uh, like uh, here is multiplicity 2, so you have two repeated roots, and then lambda equal to 2 and lambda equal to 3 are also eigenvalue. So in that case, dear student, if you can solve the homogeneous equation corresponding to lambda equal to 1. So in that case, you will get two free variables. So the this is the basis for eigenvalue corresponding to lambda equal to 1. So the dimension of eigenspace of lambda 1, lambda equal to 1 is 2. So you have to basically what you call the two like you have two pivot position, and you have two free variable. It means you have uh, two what you call two pivot position and two free row. uh, it means all of the terms will be zero, so there will be no pivot in two rows of this matrix. So the dimension in this case is 2. If we can take lambda equal to 2, in that case, if you can see over here, we have only one free variable. In that case, the dimension, which is dimension basis for the lambda equal to 2 is this column vector, and it has only one vector in that case. So the dimension space of lambda equal to 2 is 1. So in case of lambda is equal to 0, we have only one free variable, and this is column vector. This is fall in the basis of eigenspace corresponding to lambda 3. So here we have only one column vector. In that case, we can say the dimension of eigenspace of lambda is equal to 3 is again 1. So find the eigenvalues for triangular and diagonal matrix. So you have this one is a low triangular matrix. So lambda I minus a determinant equal to 0. If you have to take determinant and put this determinant equal to 0, this expression determinant. And you can see over here equal to while putting this determinant equal to 0 and solving this for lambda. So lambda is equal to 2, lambda is equal to 3, 1, lambda is, 3 is equal to minus 1. In that, for upper and lower triangular matrix, the eigenvalues are the values which are placed on the principal diagonal. If you can see lambda equal to 1, 2, lambda is equal to 2 is equal to 1, and lambda 3 is equal to minus 1. In case of upper or lower triangular matrix, the eigenvalues are just the entries on its principal diagonal. In case of diagonal matrix, so the eigenvalues are again the place on the eigenvalues are the values that are lie on the main diagonal. In that case, in case of diagonal matrix, the eigenvalues are minus 1, 2, 0, minus 4, and 3, like this. So there is no need to calculate the this expression. If you have upper triangular matrix, so the main diagonal values are the eigenvalues. So there is no need to solve uh, any equation in term of lambda. So dear student, eigenvalue decomposition problem. If you have a square matrix A and it has and linearly independent eigenvectors, then A may be decomposed in the following manner. So A can be written as V uh, diagonal element inverse of V. So where it can also where this sign basically the lambda capital lambda is the diagonal matrix whose diagonal entries are the eigenvalues of A and the column of V are the corresponding eigenvectors of this column A. In that case, you can say these are eigenvectors of A, these are eigenvalues of A, and these are again inverse of eigenvectors of A. Let us consider how we can decompose any matrix. Like if we have this one, and if you multiply V inverse A into V, then you will get a diagonal uh, matrix. So if you have like A is given and the question arises how to find this V and V inverse that make this matrix the diagonal matrix. So this is our question. So let us solve this question like to A if you have like this matrix like A into what you call it as a this one like you can go back this one. I just take this one. I just multiply this with 2 into 3, 2 into 1, this matrix, and then A into with this diagonal matrix. So what does it mean? I take just first vector, and if I multiply this with A into x v0, then A into cx, then I will get this one expression. Then if I multiply this with this, take this one only, then ultimately I will get dx and dy. In that case, if you can look over here, um, from here, if I can take just x as a common, from this I just take as a y as a common. In that case, if you can see, this is my matrix A and this is my column vector. If I A is multiply with this column vector, and x will produce and the A column vector remain same. In that case, if you recall the eigenvalues and eigenvector, AV equal to lambda time V or AX is equal to lambda time X. In that case, this the whole problem is of eigenvalue decomposition is transformed from decomposition to a eigenvalue problem. So we have to find out these values. Uh, so for that we have to solve like AV is equal to lambda time V, A minus lambda V equal to 0. So determinant of A minus lambda time I equal to 0. That is determinant of this lambda is multiplied with 2 by 2 identity matrix. So in that case, if you just subtract it and take its determinant and put it equal to 0. So you will get two eigenvalues, lambda 1 minus 1 and lambda 4. So if you could put this two eigenvalues minus 1 and 4 in this equation like this one. So ultimately your equation is transformed into finding the unknown values of a and b. So first from this you will have to solve this equation uh, for unknown values of a and C, and from this second equation you have to solve it for B and D. Thus, the V is required for eigenvalue decomposition of A. Like this, if V is like from this equation, A is minus C, and B is like B is equal to uh, 3 by 2 into D. In that case, if you can look over here, A is minus C and B is 3 by 2 into D, and C is again remain C and D is again D. In that case, if I can look over here, if you can take its inverse, so inverse of this multiply with matrix A and then the resultant matrix B, which we get from like the these are columns are the eigen vectors of uh, corresponding eigen value. So this vector is the A is minus C and C is remain C, and B is 3 by 2 into D and D is remain D. That this column vector is the eigenvectors of second eigenvalue, and this column vector is the eigenvalues of first eigen. So this vector is the eigenvector of first eigenvalue, that is lambda 1. So ultimately we will get V, and if you multiply V inverse A and V, ultimately you will get diagonal entries which are nothing, it is just the eigenvalues of matrix A. So let us take some other example, very simplest example. So how you can see over here. This example I left it as an homework. So another example, you will have to solve it in your home. Then another one. These are some very simplest example. So you will have to solve it and take it as a homework. So if you can, this end up a cubic equation like this. From this you can see the cubic equation. You will have to use synthetic deviant to find one of its what you call the uh, uh, eigenvalue. So finding the eigenvector that matches the eigenvalue minus 1. So you will have to AV is equal to lambda time V. So AV is basically XYZ, 3 is a 3 dimensional, so XYZ and minus m XYZ. In that case, you will have to solve it, and ultimately you will get V is XYZ and X is 0, Y is Y, and Z is minus Y. In that case, Y is free variable, so this is your eigenvector corresponding to eigenvalue minus 1. Similarly, you will have to test either this is correct or not. You will just multiply A with V, which is V is like the eigenvector. If multiply it with V, and you will get 0, minus 1 and 1 the same. If you take its minus as a common, and if you will get back that after multiplying this with A, and you will get an same result, that is 0, 1, minus 1 by just taking common uh, minus 1. In that case you can say, or you can just multiply AV, then you will get 0, minus 1, 1, and then lambda time V. If the result are same, in that case you can say the our eigenvalue or eigenvectors which we have calculated corresponding to this 3 by 3 matrix are correct. This is an again let the A is this matrix and eigenvalues of A is 2. Find the basis for corresponding space. Like you have A minus 2 times lambda. Lambda is here 2. So A minus 2, what you call the identity matrix of 3 by 3. I multiply this lambda with this. So I'll get this one. So 2 minus lambda I into x equal to 0. Here the lambda is 2 or so basically my matrix is 3 by 3. In that case my this column vector is 3 by 3 class 1 column vector. So in that case, if you can see over here, if we have solved this homogeneous system, so in that case, we at that point it is quite clear that that 2 is indeed the eigenvalues of A because this is equal to 0. It has only has the free variable, like it has two free variables. In that case, if you can see over here, if this can be written as in this form, so in that case we have three free variables. So and these are eigenvector, this one and this one. The dimension of eigenspace in that case will be 2 because we have two free variable and these are our eigen, what you call the vectors. So I left this as an example for you, and you will have to solve it in your home. So, dear student, ultimately, what we have did, the eigenvalue decomposition decompose a matrix A into a multiplication of matrix of eigenvalues of V and diagonal matrix capital lambda. This can only be done if the matrix is diagonalizable. In fact, the definition of diagonalizable matrix say it can be decomposed into an eigenmatrix. So it can be also be written as if V inverse A V equal to uh, diagonal matrix. In that case, this is one of the what you call the fundamental results of your eigenvalue decomposition. And fundamentally, we have the these matrix V is dear student, fundamentally the its columns are the eigen vector of uh, lambda corresponding eigen values. So V is quite important while diagonalizing matrix A into a diagonal matrix. So till then, Allah Hafiz, this is one of very simplest lecture how we can decompose any matrix and how we can find out eigenvalues and eigenvectors of any square matrix. And this has many application, and we will mainly utilize this in the symmetric and diagonalization of a matrix, and ultimately we will pursue these two concepts in image compression or singular value decomposition. Till then, Allah Hafiz, and may Allah bless you all. If you have any question, do ask me. I will inshallah answer your questions.